One of the things that we normally calculate um, when it came to Newton's laws was the weight of an object. And we know the formula for calculating the weight of an object. We know that the weight of an object is given by the formula Fg, which is your gravitational force, is equal to mg. Now here, the small letter g is what we actually are going to calculate. We're going to calculate the acceleration due to gravity on a planet. But this gravitational force can also be determined from Newton's law of universal gravitation. For example, if you take, say, for example, our planet. If we know the mass of our planet, if we know the mass of an object placed on that planet, so I'll just call this object here M1, which is the same as that there. And if I know the distance between the center of the planet and the surface of the planet, which is actually the radius of the planet, I can calculate this gravitational force. Now, the last time we actually met, which was on Thursday, we actually did this calculation for you. We actually calculated the acceleration, sorry, not the acceleration, the force of gravity on any object. And that force of gravity on an object can be now determined by this formula here. F equals to G M1 M2 over R squared. But this force here now is not just any force, it's the gravitational force of M1. So that's going to be G mass 1, which is the mass of the object placed on Earth, mass 2, which is now the mass of the planet, and R, which is specifically now the radius of the planet squared. Both these formulae represent the same thing. They both represent the gravitational force that this mass here experiences. So I can equate these two now. I'm going to get M1G is equal to G M1 MP over RP squared. MP is the mass of the planet, RP is the radius of the planet squared. If you look very carefully, you can divide this entire equation by M1. So M1 goes off on this side here, and M1 goes off on that side there. So if you divide both sides by M1, this is what you actually end up with. You end up with G equals to G MP over RP squared. Now I want to show you that this formula actually works. We know that the value for G on our planet is 9.8. So if we know the mass of Earth, and if we know the radius of Earth, we should be able to work out the acceleration due to gravity on our planet. And I want you to remember this because sometimes the examiner doesn't give this, and sometimes we don't end up looking for it on our data sheet. But the mass of Earth is actually given to you as a constant on your data sheet. Now, from year to year, the mass of the Earth actually varies. Sorry, let me rephrase that. From year to year, the examiner gives you a slightly different value for the mass of planet Earth. Sometimes they give you a very rounded off approximation of 6 times 10 to the 24. Sometimes they give you a very accurate value, which is 5.97 times 10 to the 24. So I'm going to actually end up using that. So if you go to, say, the 2023 papers, and you have a look at them, you will see that the mass of Earth is given as 5.97 times 10 to the 24. You don't have to remember this off by heart. Weirdly, I think I forgot the radius of our planet. I think it's 6.38 times 10 to the 6. I just want to double check that. Forgive me for this. Normally, I'm pretty good with these things. So if I just go to any paper, I should be able to pull out those two constants. Yeah, it's taking pretty long. All right, so here they gave us 5.98 times 10 to the 24. Not for 5.97. I saw papers where they had 5.97, so I'm going to leave it as 5.97. But that very rarely changes. 6.38 times 10 to the 6. Let me go back there. 6.38 times 10 to the 6. If I now plug that into this formula, I should come back to an answer which is very, very close to 9.8. So G, we'll now put mass of the Earth here over the radius of the Earth squared. I'm going to need your assistance. 6.67 times 10 to the minus 11. Mass of our planet, as I said, I'm gonna leave it as 5.97 because I'm almost certain KZN actually had that value last year. And the radius 6.38 times 10 to the 6. Weirdly, all provinces had the same radius. Can anybody work that out and give me the value for G on our planet now? Come, boys and girls.
9.78.
9.78. Thank you, sir. Meters per second squared, and we can quite easily round that off to 9.8, right? You need to remember this formula. You need to remember also how we get this formula. If you go through your past exam papers, I think in the year 2019, in a grade 11 paper, I'm not sure whether it was a final paper or not, they actually asked learners for the proof of this. Prove that the acceleration due to gravity on any planet is given by this formula at the end. And that's the proof for it. So I didn't just do this for no reason. It came out. Did the examiner test this? If I have any of my grade 12 friends over here, you will find that sometimes coupled with Newton's second law, boys and girls, they actually ask them something about the acceleration due to gravity on a planet because they need to bulk it up to 15 or 20 marks. So they throw in a bonus question like this for them. So please ensure you know how to use this. So what's the difference between the formulae? 90% of the questions are going to ask you something about a gravitational force. Few questions are going to ask you about the gravitational acceleration. Let me just show you this by having a look at this here. Here is a question that asks you to calculate the force between Mars and Earth. And here is the question on the gravitational acceleration of Mars. That means how fast will an object move if it is placed close to the vicinity of the surface of that planet. So you're going to get questions that relate to F. You're going to get a question that relates to G in this section. And that's why we actually did that example first, because you're going to get questions on both here. But let's start. As I said, these are what I would consider to be routine questions. They aren't very difficult. And I chose this particular batch to ease you into the formula as well. So question number 4, taken out from a past exam paper, says a body of mass 16 kilograms, boys and girls, so that's our M1 there, has a radius of 0.1 meters. The radius of this is 0.1. Made it slightly longer than the radius, but I mean, you get the idea. The distance between the surface of one object and the surface of the other object is x meters. Is placed a distance x meters from one another. Now, when they say x meters, as I said, x meters is from the surface to the surface. And the radius of the 48 kilogram object is 0.15 meters. State Newton's law of universal gravitation in words. Anybody remembers the definition or has learned it already because you're now writing in about 2 weeks from now? I just want to emphasize something, what's going to happen by this week, Thursday, going on to Sunday. Thursday to Sunday, we're going to do all the questions, probably just the really interesting ones on Coulomb's law. And then the following week, which I'm going to try and see you every day, which means Monday, Tuesday, Wednesday, Thursday, we're going to finish off electric fields. Why? Because you're writing your paper on that Friday. If your school has taken out something from the paper, let me know, please. I know that some schools have decided that they are not going to test their learners on electric fields. They are only going to do Coulomb's law because they know they're not going to get to electric fields. If that's going to be the case, please let me know in advance, because it'll also dictate the pace at which we're going to actually do these lessons. But coming back here, every particle attracts and is attracted by every other particle in the universe with a force that is directly proportional to the product of the masses and is inversely proportional to the square of the distance between the centers of the masses. Inversely proportional, square of the distance, centers of the masses are keywords towards the end of that definition. Give a reason why Newton's law of universal gravitation is said to be universal. The reason why it's said to be universal, the law applies to any two masses in the universe. Right? It is a law that can be used to calculate the gravitational force between any two masses. It is observed that the 16 kilogram body exerts a force of 2.3 times 10 to the minus 8. Note it's a very small force on the 48 kilogram body when they are placed as shown in the sketch. Write down the magnitude of the force that the 48 kilogram exerts on the 16 kilogram and give a reason. I mentioned this the last time. If the 16 kilogram attracts the 48 kilogram with a force of 2.3 times 10 to the minus 8 newtons, then the 48 kilogram attracts the 16 kilogram with exactly the same force, but in the opposite direction. Why? Because this is an example of Newton's third law, and this is basically an action-reaction pair exerted on two masses over a distance. So 4.3.1, they gave you 3 marks for that. They wanted to check to see whether you understood that concept. So the answer is 2.3 times 10 to the minus 8 newtons. And the reason? The gravitational force of attraction is an example of Newton's third law. Hence, the forces are equal in magnitude, but opposite in direction. You don't have to give such a long story, but you should, in essence, mention that it's Newton's third law and the forces are equal. Then calculate the distance x, and they gave us 6 marks for this. Now, anybody knows why they gave us the radius of the two masses before we start with the calculation? What's the reason for giving us the radius or radii of the masses? Because the gravitational force of attraction, boys and girls, is from the center of one mass to the center of the other mass. So when you're working out R is the total distance from the center to the center of the two masses. Now they've actually tested this concept quite often, center to center. And many learners have not really understood this. If R in this formula, which formula? Yeah, is from the center to the center. Anyone can tell me how we're going to now use our knowledge and the information provided to find this distance x, which is from the surface of one object to the surface of the other object? Anyone? It's actually very easy. Remember, they've given us the gravitational force. They've given us mass 1. They've given us mass 2. What should I find? Find R. And once you got R, what should you do after that to get X? Remember, R is from the center of this mass to the center of that mass. And if I want to find X, which is from the surface to the surface, what should I do after I find R? Subtract the two radii. If you subtract the two radii, you're going to get X. So the answer, 4.3.2. F equals to G, M1, M2 over R squared. The force, 2.3 times 10 to the minus 8 G is on your data sheet, but I told you it's the universal gravitational constant on Thursday. 6.67 times 10 to the minus 11. Mass 1 is 16. Mass 2 is 48. And you're going to find out the R squared over there. And for those of you that don't have the silver calculator and you can't use the equation solver, R squared is 6.67 times 10 to the minus 11, 16, 48 over 2.3 times 10 to the minus 8. And because you got R squared here, to find R, you square root both sides. You square root both sides, you end up finding R. Anybody's got the answer for R for me, please? I'm going to allow you to do this, please, because I'm not going to do everything here now.
One comma 49.
Thank you, sir. Just want to explain what 1,49 is again by just drawing a little diagram here at the bottom. 1,49 is the distance from the center of one mass to the center of the other mass. It's from there to there. That's the 1,49. The question asked you to find this distance in green now, which I'm going to highlight there, between the two masses. That's x. So what you need to do, you need to subtract the two radii from the total distance, which is 1.49. And the radii is where? 0.1 and 0.15. This was 0.1 meters on this side. This was 0.15 meters on this side. So x is 1.49 minus 0.1 minus 0.15, which gives you, I think, 1.24 meters. Please verify with me that that's the value of x.
Yes, sir.
Thank you. Now, in my opinion, that's a very easy question, but it's a question that learners normally mess up in because they don't know what to do with those radii. You find that this concept of radius addition comes up very often. And here's another typical question, but not dealing with ordinary masses anymore. It deals with two planets. One planet here is Earth, and the mass of the Earth is given to you. So there's mass 1 here. 6 times 10 to the 24. There's mass 2 here. 6.39 times 10 to the 23. And what do they tell us? The Earth and Mars are positioned in the universe such that they are 2.25 times 10 to the 8 meters apart. Look carefully now. They gave you the distance from the surface of the Earth to the surface of Mars. But you are not going to use that value in a calculation because in that formula, you need it from the center of the Earth to the center of Mars. Look, they gave us the radii. The radius of Earth, 6.37 times 10 to the 6 meters. So they gave us that distance there. 6.37 times 10 to the 6 meters. And the radius of Mars was also given from there to there. 3.39 times 10 to the 6 meters. By the way, if you didn't figure this out as yet, this is one of the reasons why we're trying to inhabit Mars. Because physically, it has the same size, it has approximately the same or similar radius. The problem with Mars is obviously the gases that they have. Right? It doesn't primarily contain nitrogen and oxygen. Its main constituent is carbon dioxide, and hence the surface temperature of Mars is much higher than that of Earth. That's what they're trying to solve when they actually go there first. Anyway, coming back to this. If they ask you what is the force between Earth and Mars, you'll take the radius plus the surface distance plus the other radius to give you the distance of separation from center to center. That's R. Right, look at this. It came out again. One last time. I'm going to do it very fast now. Every particle attracts every other particle in the universe with a force that is directly proportional to the product of the masses and is inversely proportional to the square of the distance between the centers of the masses. Calculate the force that Mars exerts. Look carefully, yeah? The force that Mars exerts on Earth. Mars is going to pull Earth towards itself. So that force is going to be directed towards Mars. 4.2 F equals to G M1 M2 over R squared. F equals to G is 6.67 times 10 to the minus 11. The two masses, 6 times 10 to the 24, 6.39 times 10 to the 23, and the distance. My suggestion is put it all inside the bracket and square it all together. Radius of the Earth, remember that's in meters, that's not in kilometers. So it's 6.37 times 10 to the 6 plus 2.25 times 10 to the 8 plus 3.39 times 10 to the 6. You add all of that up and then you square it. Answer, please. That should be a huge force.
1,6.
Oh, that you just broke up there. I didn't hear the whole thing. Somebody else with a bit of a clearer mic. Guys, come please. Somebody work that out now. Guys, I don't have a calculator. You got a calculator there. Please punch it in and give me the answer.
4,64 times 10 to the 21.
Thank you, sir. 4,64 times 10 to the 21 newtons. And because it just said force, you have to say that that force on Earth is directed towards Mars. Now that's a massive force. These are the forces that keep the planets in their positions and locked in their orbits. Right. Is the force calculated in 4.2 a contact or a non-contact force? It's a force that is acting over a huge distance. Obviously, it's a non-contact force. Then calculate the acceleration due to gravity on Mars. Weirdly, the acceleration due to gravity on Mars is not close to 9.8 at all. It's actually much lower. That means we'll find things quite easy to do in Mars. For example, walking. Because the Earth is not going to pull us with such a large force. Sorry, Mars is not going to pull us down with such a large force that Earth will be able to do. And that is due to the fact that the acceleration due to gravity is much smaller. So it's going to be 6.67 times 10 to the minus 11. This formula is also on your data sheet, by the way. So if you don't want to learn how to derive it and risk that you won't know it if it does come out, if the derivation does come out, you can just remember the formula from the data sheet. M is the mass of the planet, and here it's going to be the mass of Mars. 6.39 times 10 to the 23. And the radius of Mars was 3.39 times 10 to the 6. And we're going to square this. Anybody's got an answer for the acceleration due to gravity on Mars? If I remember correctly, it's about 3. About 1/3 that of the Earth. So about 3.3, I'm guessing.
3.7.
3.7. What are the two decimal places, please?
3.70.
70. Okay. Meters per second squared. It's an acceleration you're calculating, so it has to have a direction. So it's 3.70 meters per second squared downwards. It will be downwards towards Mars, obviously, in this case. And then the last question, which they asked in the previous one as well, because learners don't seem to understand this. What will be the force that the Earth exerts on Mars? The Earth will pull Mars with exactly the same force. And the force is 4.64 times 10 to the 21. There's no working out for that. And that will be directed towards Earth. But if you have any questions, please ask, because I'm going to go to the next one, and that's going to be slightly more involved than this previous one. Anyone? No one. But lovely. The other thing I want you to note is I've deliberately selected these examples for the ease of calculation and the fact that it's not too difficult. Right? There are more difficult questions than this in this section. I'm hoping that we can do one or two of them on Thursday and also make a start with Coulomb's law on Thursday. Right. The next question. Again, you are dealing with large objects here. And if you're dealing with a large object like the Earth, please don't forget that you're going to take it from the center of the Earth to satellite A, or from the center of the Earth to satellite B. Now note, I'm not talking about the center of the satellite. I don't need to know the length of the satellite. For example, anybody knows why we don't really worry about the center of very, very small objects compared to planets? In other words, why we don't get finicky or ask you a question like, what is the distance from the center of the satellite to the surface of the satellite? Why do they not give that to us? Because that radius there is so small that we can assume that the entire satellite is actually just one point. And that satellite is also just a point. So when do radii play a real role? The truth is, you only need to know the radius when the masses are really large. But otherwise, if the masses are relatively small, right, we actually can leave them out. But two satellites orbiting the Earth are situated on opposite sides of the Earth. Satellite A has a mass of 3,800 kilograms. So that's mass 1, 3,800 kilograms. And satellite B has a mass of 4,500 kilograms. Satellite A is at a height of 25,000 kilometers above the surface of the Earth. The surface of the Earth. That means from there to the satellite. That's 25,000 kilometers. Converting that to meters, it'll be 25,000 kilometers multiplied by 1,000, which is 10 to the 3. That's in meters. You still have to add on the radius of the Earth. There. And the radius of the Earth, if you check this thing, it should be about 6.38 times 10 to the 6 meters. It'll be on your data sheet, so you will look for this value to use. Again, Newton's law of universal gravitation was tested. I'm not going to give you the definition again. So you can be guaranteed this is coming out in your paper. Anybody wants to describe what weightlessness would be? When does an object experience weightlessness?
So isn't it when the object's in free fall and the only force of gravity?
Actually, no. Weirdly, an object will experience weightlessness when the gravitational force acting on it is zero. And when can a gravitational force be zero? Let me talk about this because this is where the questions get difficult. So let's assume I have object A here. It's applying a gravitational force on object B. So A is pulling B towards itself. That's the force that A applies on B. Then C on the other side is also going to apply a gravitational force on B. Why? Because C is another mass, B is a mass. C is going to attract B in that direction. That's the force that C applies on B. If these two gravitational forces are equal in magnitude and opposite in direction, B will have a net gravitational force which is zero. And when you experience a net gravitational force which is zero, you are actually technically weightless. When do you experience this technically if you are an astronaut? You experience this when you go into outer space and the other planets exert the same gravitational force on you that the Earth is currently exerting on you. And that's why you actually float. Is because all the other planets combined are pulling you away from Earth. Earth itself is trying to pull you towards itself. And those two gravitational forces cancel out. And then you experience what we refer to as true weightlessness. So it's quite a complicated thing, weightlessness. We, in our lifetime, well, maybe you may get lucky, or me, for example, I won't be in a position to actually experience that in its really true sense. I don't know, maybe Elon Musk will actually develop the technology very quickly where you can actually do these space holidays, he calls them now. Right? You can actually visit outer space in an ordinary aeroplane. That would be really cool. Just on that note, what's really interesting, he is also in the process of developing a system of going out into space and then traveling back down towards Earth to any other part of the Earth. And you can travel from wherever you are to any other part of the Earth in only 2 hours. You should read up on that. There's actually a nice video on that. That from one point on Earth into outer space and another point back into Earth will only take you 2 hours. So you're not basically working with the Earth's gravitational field. You're going out of the Earth's gravitational field and then going back in again. So, weightlessness, the net gravitational force on an object is zero. Calculate the force between Earth and satellite A. So, remember we said it has to be from the center of the Earth to where the satellite is. So you take the surface distance to the satellite, add it to the radius, and you'll get your distance of r, which is your distance of separation between the satellite and the Earth. So F equals to G m1 m2 6.67 times 10 to the minus 11. Mass 1 is the mass of the satellite, 3,800 kilograms. Mass 2 is the mass of the Earth that they give it to us. No, they didn't. We're going to get that from our data sheet, I'm just going to take the value that I think you're going to find, which is the most current value or popular value rather that they use for the mass of the Earth, which is 5.97 times 10 to the 24. That's the mass of the Earth. And then the distance of separation between them is the 25,000 kilometers they gave you. So 25,000 multiplied by 10 to the 3 will give you, I'm going to rewrite this as 2.5 times 10 to the 7. You can double check that. Plus the radius of the Earth, 6.38 times 10 to the 6. And you're going to square that. Anyone?
One five three six comma 66.
You have to say it a bit loudly, sir.
1536 comma 66.
Is that right?
Yes, sir.
Thank you. Go back again and read it carefully. Calculate the force between the Earth and satellite A. So if it says between, it's not giving you a particular direction. You will say towards each other. Because they're not talking about any one of the particular or planets in particular, or the planet or the satellite. Right. Now comes the next question, which is an interesting one. What distance above the surface of the Earth should satellite B be to experience the same force as satellite A? Choose from greater than, less than, or equal to the distance above the Earth, and explain how you arrived at the answer. They don't want you to do an exact calculation here. They are simply asking you to tell us whether this distance, the black distance there, is going to be greater than or equal to or less than this distance here between satellite A and the Earth. Anyone? If the two forces are the same, and now your two masses are going to be the mass of the Earth, which you've used before, the mass of the satellite, which is now M2, 4,500, which is bigger than 3,800. What can you say about the distance between the Earth and satellite B if two forces are the same? It can't be the same because the second mass is larger, isn't it? So what must the distance be so that the forces now are the same? Anyone? Must this distance in green from there to there be bigger or smaller than the red distance, which is the distance from here to there? Now, because you got a bigger numerator, why bigger numerator? Because your 4,500 is bigger than your 3,800. You're going to need a bigger denominator as well to compensate for the bigger numerator you're going to have. Otherwise, the two forces can't be the same. And if you're going to have a bigger denominator, that means you should have technically a larger distance of separation. So it should be greater. The mass of B is greater than the mass of A. So your force is directly proportional to the product of the masses. Therefore, if M1 times M2 for mass B is larger, the numerator is larger, which implies then that R has to be large as well to compensate for the larger numerator. Therefore, the distance is bigger. All right, boys and girls, we're going to stop over here. On Thursday, unfortunately, we don't have much time to actually do very, very fancy questions here as a group. So I'm going to just move on to Coulomb's law on Thursday. Right? There are some questions that I did leave out. I'm hoping that I'll have some time maybe on that Thursday night before you write to actually do some additional examples with you. Right, but we're actually going very, very close now to the exams. And I'm hoping the people that are writing, especially the DHS and George Campbell learners, are actually here so that they can actually benefit from these additional lessons we're having. I'll send a link for the video to everyone, and you can please watch it today, because this is going to be technically your last group lesson over here on universal gravitation. And if your school, as I said, is cutting the paper down for some reason, do let me know, because it will also dictate on how fast we need to proceed as well. Thanks for attending, people. So let me just get the one more person, the use of that. See you at the next lesson.